Welcome and thank you for joining. In this lesson, we'll explore the derivatives of logarithmic functions. We'll start with the proof of the simplest logarithmic function, y equals log with base a of x, and we'll do this by using the first principles formula. If f of x equals log with base a of x, then we'll say that f prime of x would equal the limit as h approaches 0 of f of x plus h. So remember, instead of x, now we have x plus h, which will turn log with base a of x into log with base a of x plus h, right? So we'll write that down first. And then minus, so this minus here, f of x, well, f of x is simply log with base a of x, and then that will be divided by h. As you can see here, substituting h by 0 will make this expression inside the limit undefined. So this is an indeterminate form limit. And the way that we have simplified or evaluated indeterminate form limits has been by simplifying the h which is in the denominator, because that's the one that becomes 0 and makes the expression undefined. So the way that we've done this in various types of functions has been by either breaking every term down into smaller parts and then rearranging and simplifying, remember conjugation, remember factoring, etc., or by simplifying or bringing the terms together. So every equation or every function will be different. So in this case, what we are going to do is try to simplify the numerator. So as you can see here, we have the difference between two logs. So log is another name for exponent. So when we subtract exponents, it means that we have divided exponential numbers. So according to the quotient law of logarithms, then we are going to rewrite the numerator as log with base a of, so divide the expressions inside the log. So that means x plus h divided by x, and all this over h. So I will rewrite the numerator slightly differently. So we have the limit as h approaches 0. We have log with base a of, now I will assign the denominator x to each term in the numerator, which means that we'll have x over x plus h over x. The denominator still has h. Now notice that here we have a new term, h over x. X over x will become 1. And we will bring h over x in the denominator as well. And we'll do this by multiplying h by x over x. So in the next step, we'll simplify some more. Limit as h approaches 0. We have a big fraction line, the log with base a. Inside the brackets, we'll have x over x, which is 1, plus h over x. And then close brackets. And down in the denominator, we'll combine this h with this x down here to make an h over x. Remember, in multiplication, multiply tops together, bottoms together. You can arrange them in any way you want. So that will turn into h over x and then times x. So now that we brought in the same term, h over x, what we'll do is replace this by a single variable because it makes the expression a bit awkward. So instead of h over x, we're going to use the variable p. Now, if h over x equals p, then we'll say that when h approaches 0, then h over x will also approach 0. In other words, then p will approach 0. So that means that we have the limit log with base a. We have 1 plus p over, down here we have p. And the reason why I mentioned the value of p in here is not only to emphasize the fact that p is the one that is carrying this h value in here, but also that because we need to actually replace h as well in here, because if this is the changing number in the equation of the function, then this must be reflected in the value where the limit is approaching, the independent variable, the limit is approaching to. So they have to match, because it makes no sense to say h approaches 0 when you don't see an h in here, because we can assume that is some constant or who knows what. So the other term that we have in here is the term x. So a couple of rearrangements that we'll make in the next step are the following. So we'll have the limit as p approaches 0. And I will be rewriting this expression again slightly differently. So as you can see here, we have x in the denominator. So this is a factor in the denominator. And we can bring this factor outside this entire fraction as 1 over x. So if we are dividing by x or multiplying by 1 over x, is the same thing. And on the other hand, then we're going to bring log with base a of 1 plus p in another fraction. So we'll assign a new fraction 9 for it. And then you see that we have also the coefficient p in the denominator. So we'll bring this to the front. So this will be 1 over p. And that will multiply the expression log with base a of 1 plus p. So again, in the next step, a couple more changes. So first of all, since we have the product of two, or the limit of the product, then we're going to break it down into the product of limits. So that means we'll have the limit as p approaches 0 of 1 over x, and then multiply this by the limit as p approaches 0. Let's be consistent with our colors here. And here we have 1 over p as a coefficient of this expression here. This expression is a log expression, right? Or a log term, to be more precise, because it's a single monomial. So 1 over p is a monomial that is multiplying a log, and according to the power law, we can bring this inside the log expression as an exponent. So we're going to rewrite this as log with base a of 1 plus p to the power of 1 over p. So again, what we are trying to do here is bring this 1 over p up here as an exponent. That's because it's a multiplier of this log term. So let's see what we have obtained in here. So as you can see, 1 over x doesn't depend on p at all, because p depends on h, basically, because h over x approaches 0, p approaches 0. So therefore, we're going to say that 1 over x can come outside as sort of a constant. So we'll say that we have 1 over x. That would be the value of this limit. And then we have the limit as p approaches 0 of logarithm with base a of 1 plus p to the power of 1 over p. So we have simplified this to the best we can, and at this point, we don't know how to evaluate this. We do know that if we substitute p by 0, even though we don't have the fraction anymore, right, the denominator here anymore, we still have the value of p here that can be potentially 0 and make this undefined. And if the exponent is undefined, the entire expression is undefined. So in this case, what we do is we give p values close to 0. So we start at 10, 1, 0.1, and so on. And we'll do this by using decimals, actually. So I brought this on decimals. So I'm going to look at it together. So this is a function y equals 1 over x to the power 1 over x. We give x values from 10, 1, 0, 1. And if you go all the way down here at x equals 0.000001, you see that the numbers start stabilizing. So they start actually right here at 0.001, 2.71, 718, 7182, 71828, and so on. So the values of y become 2.71828, and you probably recognize a famous number here. And this would be the number e. So that will allow us to write this limit as 1 over x, the log with base a we know what this expression becomes as p approaches 0. It becomes the number e, so it becomes a constant number. So we'll write e right here. So it seems that the derivative of log with base a of x is 1 over x log with base a of e. Still a little bit confusing to memorize it as a formula, so we'll write it in a neater form. So we have 1 over x, and we'll rewrite this term, this log term, differently by using what we call the change of base formula. So the change of base formula allows us to split the base and the exponential number and write it in fraction form as log of e over log of a, as long as we provide the same base to both numerator and denominator. So the base that we are choosing in this case would be the base e. So that would be equal to, again, we have 1 over x. Now, log with base e of e is equal to 1 because log with base any number of the same number is 1. And log with base e of a, remember that log with base e is practically ln. So whenever we write ln, it's logarithm with base e of a. And this is the most simplified form of f prime. So with this, then we're going to say that the derivative of log with base a of x is equal to 1 over x ln of the base. And voila, here goes the formula for the derivative of log. Now, based on the derivative of log with base a of x, we'll derive the derivative for ln of x. Now, remember, ln of x is nothing but log with base e of x. So when we differentiate this, then we'll say that this would be equal to 1 over x, so this expression you have inside the brackets, and then multiplied by ln of whatever the base is. In our case, the base is e. But we know that ln of e, because it represents a log with base e of e, would equal 1. So that means that that would be x times 1. And we'll say that dy dx equals 1 over x. So therefore, the derivative of ln of x equals 1 over x. And this is the second formula, my more favorite formula when it comes to derivatives of logs. As you can see, it's very simple, very easy to memorize, just like e to the power of x, which has the derivative equal to e to the power of x. Ln of x has the derivative, very simple, very easy to remember, 1 over x. So these are the two formulas for the log functions. This is the proof for y equals log with base a of x. I hope this made sense, and I hope that you enjoyed going through this proof together. Bye for now. We'll continue with examples in the next video.